Hey everyone, welcome to today's Explainer. We're going to dive straight into something literally everywhere around us, motion. Imagine we've got a giant blank whiteboard right here between us, okay? We're going to sketch these concepts out step by step so they make total sense. You ready? Let's get into it.
Here's our quick roadmap for today. We'll hit 1. Motion all around us. 2. Finding the reference point. 3. Distance versus displacement. 4. Speed, velocity, and acceleration. 5. Uniform circular motion. And finally, 6. Recap and practice time.
Okay, part 1, motion all around us. Let's start with linear motion. Just moving in a simple straight line. I'm going to draw a highway on our board here. Now, put yourself in a car cruising down this highway. If the truck right in front of you suddenly slams on the brakes, how do you figure out the exact safe distance you need to not bump into it? Does it change depending on your speed?
If you're the one sitting in that car we just drew, you absolutely can't just guess that distance. To really figure it out, we actually need a solid, clear system to describe exactly where the car is in the first place.
Which brings us to part 2, finding the reference point.
All right, let's draw a nice, big, dark dot right in the middle of our board. We're going to call this origin O. That right there, that's our reference point. Anytime we want to describe where something is, we use this fixed point. So if an object's position changes compared to this exact dot over time, boom, we know it's in motion. It's basically our anchor.
Next up, part 3, distance versus displacement. Let's draw a little path here to show you a tricky concept. A lot of people get stuck on this, so keep your eyes peeled. How far you've traveled actually isn't always the same thing as where you end up. Let's sketch a quick number line. Imagine an athlete, let's call her Nina. She starts her run right at our origin, point O. She runs all the way out to point A. Let's mark that at 100 meters. But then she turns around and runs back to point B, sitting right here at the 40-meter mark. Let's divide our board right down the middle to compare. First, distance. This is the total path she actually ran. She went 100 meters out to A and then added another 60 meters running back to B. So her total distance is 160 meters. But displacement? Well, that's completely different. Displacement is just the net change from her start to her finish line. She started at O and she ended at B. That net change is just 40 meters.
So here is the absolute most important takeaway. Displacement is that net change in position. But check this out. It requires a number, which we call magnitude, and a direction. It's what we call a vector quantity. You can't just say 40 meters. You have to say 40 meters in the positive direction. You see, distance is just a plain number, but displacement, it always needs that directional arrow. Make sense, right?
Moving on to part 4, speed, velocity, and acceleration. You're doing awesome. Let's draw a little clock on the board now to see how fast we're actually moving. Here's another super important comparison to draw out. Average speed is just your total distance divided by your time. Simple enough and no direction needed. But average velocity? That is your displacement divided by time. And since we just figured out that displacement has a direction, well, velocity has a direction too. A simple plus or minus sign tells us exactly which way you're headed.
Okay, but what if your velocity isn't staying perfectly steady? Say I sketch a car moving straight ahead, and its velocity keeps going up, or maybe slowing down. That's what we call acceleration. It's literally just the change in velocity divided by the time it took to change. To calculate this on your own board, just follow these quick steps. First, jot down your initial velocity. We'll call it U. Then your final velocity, V. Find the time it all took, T. Now, just subtract U from V to get your total change in velocity and divide the whole thing by T.
A really great real-world example to draw here is just dropping a ball. If you let it go, it doesn't fall at some boring, constant speed. It actually gains speed constantly, exactly 9.8 meters per second squared. We call this the acceleration due to gravity, or just a lowercase g.
Let's jump to part 5, uniform circular motion.
All right, let's take our eraser, wipe away all those straight lines, and draw a perfect circle. We're going to throw a really cool curveball here in physics. Picture an athlete running on this circular track at a perfectly constant, steady speed. Imagine their speedometer just isn't moving at all. So, here's a question for you. Are they accelerating?
Believe it or not, yes, they are. Even if their speed never changes one bit, think about the direction arrows we draw for them. The direction of their velocity is changing at every single instant to keep them right on that curve. Since their direction constantly changes, their velocity constantly changes. And anytime velocity changes, you guessed it, they're accelerating.
Okay, part 6, recap and practice time. We really covered a lot of ground today. Grab your notebook and jot these down. Number 1, motion always needs a fixed reference point. Number 2, displacement is your net change in position, totally different from total distance. Number 3, velocity is displacement over time, which means it definitely needs a direction. And number 4, acceleration is any change at all in that velocity. Now it's your turn. Give these practice problems a shot on your own using the step-by-step logic we just sketched out. First, try finding the displacement of a student who walks up to the 4th floor, then back down to the 2nd floor. Remember, displacement only cares about where you start and where you finish. Next, find the average acceleration of a car speeding up from 0 to 24 meters per second in exactly 6 seconds.
I'm going to leave you with one final puzzle from our lesson to chew on. Say a girl is riding her scooter, and her speedometer reading is completely constant. Is there any possible way her scooter is actually accelerating? And if so, how? Maybe think back to that circle we drew. I really hope you had fun sketching out these concepts with me today. Keep an eye out for all the incredible motion around you, and I'll catch you in our next explainer.